Hello everyone, my name is Daehan Kim. I'm a practicing kinesiologist. My main role is to help people adapt certain behavioral movements that are ideal for their specific needs and goals. I mainly work with people who are either recovering from the recent injuries, had past injuries that still bother them, or are dealing with chronic conditions such as arthritis, cerebral palsy, or fibromyalgia. As most of my clients are dealing with complex mechanical and pathological issues, I often collaborate with other practitioners such as physiotherapists, chiropractors, osteopaths, massage therapists, or physicians who are pain specialists and physiatrists. Over the past several years, it has become clear to me that it is necessary to incorporate movement training strategies into clinical practices, as both the healthcare and fitness communities have been under increasing pressure to help people adopt healthier movement behavior while at the same time preventing them from getting back into their compensatory behavior patterns. We have been using so called corrective movement strategies to achieve this goal. On the surface, these corrective movement methods appear to focus on improving mechanical aspects of movement, but at a deeper level, the ultimate goal is to help the central nervous system improve how it perceives and plans movement. In addition, we have seen a significant amount of neuroscientific discovery over the past decade that can be used to advance current methods of movement training. I was fortunate enough to have been involved in some of the research on sensory motor neuroscience, and I also taught subjects dealing with motor control for 4 years at the University of Saskatchewan and Simon Fraser University before beginning my practice as a kinesiologist. In doing this work, I hoped to contribute to the collective effort of translating the neuroscientific knowledge into the field of movement training. In this webinar today, I will review the current understanding of the way in which the central nervous system induces motor adaptation, focusing heavily on the factors that drive the adaptation. Then, I will discuss how we can use this knowledge to advance current movement retraining strategies. Before we talk about the scientific theories underlying the human motor adaptation, let's think about the following situation. You borrowed a friend's computer but found that the mouse setting is different from what you are used to. It doesn't have a scroll wheel, and the mouse moves the cursor faster than you expected, making it difficult for you to control the mouse accurately. What causes the resulting errors? The computer? Probably not. Our incorrect prediction regarding how much the mouse cursor would move relative to our arm movement is what caused the error. However, it doesn't take long time for our brain to adjust both our prediction and the amount of the arm movement in order to regain the accurate control of the mouse. It was necessary to adapt our movements. Therefore, we can say that the adaptation is the process of reshaping our prediction and movement planning in order to minimize the mismatch between our prediction and the consequence of our action. A similar concept was proposed as the theory of the internal model in 1943 by a Scottish psychologist, Kenneth Craik. According to Craig, our brain contains a small-scale model of external reality which acts as a simulator that allows us to predict consequences of various actions before they actually happen. He said that our activities give this simulator opportunities to compare its prediction of what will happen with actual consequences. Based on this comparison, this internal model continuously evolves so that its ability to predict becomes accurate enough to allow us to interact with a rapidly changing environment in a safer and more competent manner. As a result of other neuroscientific research, it has become even clearer that what Craig called the internal model actually exists. And we are now at the stage where we can actually map out the brain regions for the internal model. There is evidence that when we intend to move, the motor cortex sends out a copy of a movement plan to other regions of the brain before the movement occurs. The brain regions that receive the copy of the movement plan work like predictors. One of the representative regions of the brain used for the prediction is the posterior parietal cortex, which is actually a sensory cortex. The basic role of this region of the brain is to integrate various sensory information such as vision, touch, joint position change, or body equilibrium. Therefore, we are able to predict upcoming sensory feedback that follows movement. That is why such prediction is called sensory prediction. When sensory prediction does not match the actual feedback, we say that there is a sensory prediction error. How is the error detected then? A neural signal of sensory prediction is also delivered to other regions of the brain that are responsible for comparing predicted and the actual sensory information. One of the representative regions of the brain is the cerebellum, which seems to be strategically positioned to work like a middleman between the cerebrum and the spinal cord. Information regarding the errors in sensory prediction are fed back into the circuits within the cerebrum, which allows us to calibrate our prediction or, if necessary, the motor planning itself. It is important to address that the studies on monkeys and cats, not humans, provided the direct evidences for such a structural arrangement for the internal model. Nevertheless, many behavioral studies on human clinical population have strongly suggested that the similar structure of the internal model exists in human brain. The theory of the internal model tells us that the most important role of adaptation is to help us ensure our very survival. However, it seems like the modern society is suffering from the cost of adaptation rather than truly enjoying the benefit of the adaptation. Postural maladaptation associated with too much sitting or driving is a very common example of this. Interestingly, trying to maintain a good sitting posture based on our understanding of biomechanically correct posture doesn't seem to help with preventing such an undesirable adaptation. I suppose then we must ask if it is even possible to choose not to adapt when our environment calls for such an adaptation. Let me talk about research evidence which shows that the adaptation is so ingrained in our brain that we may not have conscious control over it. Box A demonstrates typical patterns of adaptation. In this particular study, participants were instructed to reach the green target with the cursor controlled by their occluded hand. The hand that moved was hidden under the table, and the cursor on the monitor represented the location of the sensor attached to their fingers. The sensor was manipulated such that the cursor movement was shifted 30-degree counterclockwise from the actual movement. As expected, the participants started to miss the target 30-degree counterclockwise at first. However, as the participants repeated the task many times, they learned to aim 30-degree clockwise to hit the green target, which is represented in the figure on the right side. Now, let's talk about the box B. The researchers replicated the research shown in the box A on other participants. However, this time, the researchers instructed the participants to deliberately aim 30-degree clockwise to hit the target because the sensor is manipulated. This explicit strategy worked very well at first, and the participants were able to hit the target during the first few trials. However, as they repeated the trials, they started to missing the target further and further clockwise. The participants became increasingly frustrated as they had no idea why they kept missing the target. Some even thought that the researchers have lied to them. What was happening? The only explanation was that the sensory motor adaptation occurred non-intentionally. The same non-intentional adaptation occurred in another study utilizing a different type of adaptation where participants' reach trajectories were manipulated by a direct force to their hands. As a result, it was eventually suggested that the motor adaptation is implicit, meaning that it is non-intentional, automatic, and occurs without one's awareness. What drives such an implicit adaptation then? The researchers replicated the same experiment again, but this time they recruited participants with cerebellar deficits. The result was completely different compared to that of the experiment on the healthy population. Box A shows that the participants failed to achieve typical adaptation without being given an explicit strategy, missing the target counterclockwise throughout the trials. Box B shows that when the explicit strategy was suggested, the patients reached the target throughout many repetitions, indicating that implicit adaptation did not occur and that an explicit strategy dominated. What are the implications? If we relate this to the mechanism of the internal model, we see that the cerebellum is what recognizes the mismatch between the expected cursor location and the actual cursor position, which is essentially the sensory prediction error. Therefore, the results suggest that the mechanism underlying implicit sensory motor adaptation is the sensory prediction error. We can therefore say that we should be able to facilitate motor adaptation of an individual if we can create sensory prediction error for them. There are tools and devices that are currently used to alter sensory information. For example, there are prism goggles that shift the visual field in a certain direction, a split belt treadmill that can create asymmetric demands on our gait, and a virtual reality system that creates a discrepancy between the perceived and the real movement. I think these devices and tools can be used to improve specific biomechanical patterns of movement. For example, it was anecdotally observed that the osteokinematic behavior of the hips changed when the participants were asked to walk straight while wearing a prism goggle, and all the participants showed similar patterns of the change. I would love to see more research on the effect of the sensory modification on the biomechanics of the movement. Why is it important to know that the motor adaptation is implicit? We often give our patients or clients instructions regarding proper muscle activation or joint positioning, hoping that it would facilitate an adaptation towards correct movement mechanics. However, we have a dilemma here, as we just learned that such explicit strategies don't have much control over the implicit motor adaptation. But we still need to use verbal instructions and cueing to help people understand what we hope to achieve. Then, is there a proper way of using instructions or cueing? The author of the book Attention and Motor Skill Learning, Professor Gabrielle Wolf from the University of Nevada, and her research group suggested that verbal instruction and cueing that draws conscious attention to the internal process of movement, such as muscle activation or joint mechanics, would interfere with the implicit motor control process. They suggested that it would be more effective to use external cues that draw attention to the expected movement outcomes or goals. These suggestions were well supported by much other research evidence on motor skill learning of novice athletes. Examples of such internal cues that can be disruptive to the implicit adaptation are push your hips back or activate your glutes in the case of the squat exercise. Examples of more effective external cues can be sit back into an imaginary chair or push the ground to stand up. It was also suggested that if we explain the internal process of movement before the practice, it may help people understand the context for the practice. Therefore, I cannot overly simplify this concept and say that the internal cues are bad and the external cues are good. But it is necessary to think about how we should verbally guide our clients without sacrificing their central nervous system's natural ability to induce an adaptation. Let's look at an example of how we are currently helping patients and clients improve their body dynamics using a tool. When someone habitually collapses his or her knee medially, when loading the body weight onto one leg, we can use a TheraBand that pulls the knee even more medially. As a result, the person can reactively push against the band, thereby correcting this misalignment. This method, commonly known as the reactive neuromuscular training, sometimes even works like magic because the client immediately shows improved alignment of the knee. However, such benefit doesn't easily transfer to the movement without the TheraBand, which indicates that the immediate improvement is the only a temporary adaptation specific to the TheraBand. In response to the TheraBand, the central nervous system somehow came up with the motor commands, which are more desirable for controlling the lower extremity. What we really want is for the person to be able to achieve the same motor commands without the TheraBand, as it is more transferable to other contexts. How can we maximize the potential for such a transfer when using while using the TheraBand for training? To do so, we need to know a little bit more about how the central nervous system generates the motor commands. A motor command A motor command is a selective neuronal discharge from the motor cortex based on the central nervous system's estimation regarding how much force is needed from each muscle fibers to induce a desired kinematic change of the body, such as the angle of movement, trajectory, distance, or acceleration. The effect of force generation on the kinematic changes of the body is defined as body dynamics or dynamic response of the body. Body dynamics can be understood cognitively. It is represented as a mathematical equation on the slide. It is important to know the variables that affect dynamic response of the body given the same amount of force. The examples of these variables are weight and length of the segments to be moved, or extensibility of our soft tissues. We can appreciate that the value of these variables often changes as we use different manual tools such as a tennis racket or a hammer. In addition, growth, development, the aging process, or injuries also often affect changes of these values. If we have to measure these values every time they change, the process of estimating the required muscle activation is extremely slow, and it will be impossible to control our movement in a timely and precise manner. It was suggested that implicit adaptation represents the central nervous system's effort to solve the problem of delayed cognitive understanding of body dynamics. For example, constant calibration and instantaneous updating of motor commands automatically accounts for the changes of the value of the important variables such as weight or length of the segment, or the extensibility of our soft tissues. Importantly, it was also suggested that continuation of the implicit adaptation may allow the central nervous systems to form a neuronal model of a task-specific body dynamics, which is somewhat different from the cognitive understanding of the body dynamics. Such a model of body dynamics can be expressed as a neuronal representation within the motor cortex. For example, in vivo studies on primates found that the motor cortex is capable of forming directional preferences within its neuronal cells after repeating a certain task many times. And it was argued that such directional preferences can work like a convenient lookup table for forming synergistic muscle activation. If we relate this back to the reactive neuromuscular exercise I talked about a few slides ago, the ultimate goal we want to achieve through this exercise is to update the neuronal model of body dynamics, which essentially improves the synergistic muscle activation for controlling our own body without having to rely on a tool or equipment. How can we maximize the potential to achieve this when using tools or equipment for the training? To do so, it is important to understand that when the central nervous system recognizes that there is a movement error, it needs to estimate the causes of the error. The sources of the errors can be extrinsic, such as equipment used, or it can be intrinsic, such as intensity and timing of the muscle activation. If the central nervous system attributes the error to the extrinsic sources, it makes adjustments specific to the equipment used or the environmental conditions. If it determines that the source of the error is intrinsic, it tries to update its neuronal model of the body dynamics. It is known that there is always some degree of error coming from the intrinsic sources, even for a simple movement such as reaching. This is because some degree of error is expected in the process of delivering the neural signals from our brain to the muscles and converting those signals into muscular activation, which scientists often call a motor noise. Therefore, in our daily environment, both extrinsic and intrinsic sources cause movement errors. Instead of treating the contribution from the extrinsic and intrinsic sources in all or nothing manner, the brain has to find a way to weigh the relative extent of contribution and combine both of sources in an optimal way. It was suggested that our central nervous system determines the relative extent of contribution from the extrinsic versus the intrinsic sources based on the variability of each component experienced. Based on such evaluation, the brain prioritizes the adaptation towards less variable factors, which makes sense as less variability also means more predictability, and our brain likes to predict. The researchers who suggested such a principle used used a force field adaptation protocol where the participants reached to a target while holding a robot handle that generated the force which shifted their reach trajectory, which was somewhat similar to a TheraBand exercise we often use. Let me explain the experiment more in detail. In this experiment, participants performed reaching tasks while holding a handle attached to a robot arm. The robot was programmed to generate forces clockwise as they reach forward, as the participants reach forward, thereby inducing movement error towards clockwise direction. After performing the trials many times, the participants adapted to robot's force and was able to move their hands relatively straight. After achieving such adaptation, they were asked to reach without being perturbed by the robot force. These post-adaptation trials were performed in two different conditions. The first condition was named free condition, meaning that the robot arm was detached from the handle. Therefore, the participants knew that there was no perturbing force anymore. The second condition was called robot null condition. In the robot null condition, the handle was still attached to the robot arm, but the force was turned off. Therefore, the participants were able to move the robot arm freely. In the robot null condition, the participants were given a verbal explanation that the force of the robot arm was turned off. The graph on the lower left shows the magnitude of the reach error per each trial. The black dots indicate that the participants showed typical adaptation pattern where they first made huge errors and eventually learned to compensate for the forces from the robot. The green dots and blue dots on the right side of the black dots show after effects during the post-adaptation period in two different conditions. Notice that the direction of the error was the opposite of the direction shown during the initial adaptation period. So the after effect in this case means that the participants were still compensating for the experimental perturbation even after such perturbation was removed. The green dots indicate the after effect during the free condition, where the handle was detached from the robot arm, and the blue dots indicate the robot null condition, where the robot arm was still attached but the force was turned off. Now notice that the magnitude of the after effect was significantly smaller when the handle was detached from the robot arm than when the handle was attached to the robot arm, which is depicted in the graph on the lower right hand corner. Well, in both conditions, the force from the robot did not influence the participant's movement. Then, how come the magnitude of the after effect was relatively smaller when the robot arm was detached from the handle? To understand what this relatively smaller after effect implies, we can think about the definition of the after effect again. After effect means that participants inappropriately used the newly updated internal model for the condition that such an adaptation is not applicable anymore. Therefore, the fact that the participants were able to reduce the magnitude of the after effect when the handle was detached from the robot arm means that the newly updated internal model was more associated with the robot arm than the dynamics of their own arm. In other words, it means that the participant's central nervous system attributed the movement errors that occurred during the adaptation period more to the dynamics of the robot arm than their own body dynamics. This makes sense because the perturbing force was generated by the robot arm, right? So does that mean that whenever we experience adaptation while using a tool or equipment, the central nervous system always prioritizes the external forces than the internal model of our body dynamics when determining sources of the movement error? Not necessarily. It was further suggested that our nervous system modulates such prior, prior, prioritization based on the variability of the perturbing forces. The following experiment provides evidence for such an idea. The experimental setting for this study was the same as the previous experiment, but this time the participants were divided into two groups and adapted under robot's force with two different variability. The first group underwent the adaptation trials with the force of the robot arm gradually increased after each trial, meaning that the perturbing forces had relatively higher variability. The second group went through the adaptation trials with the force of the robot arm abruptly introduced and remained the same throughout the trial, meaning that the variability of the force was low. The researchers called the first group gradual group and the second group abrupt group. After the adaptation, both groups were tested in the same post-adaptation condition where the handle was detached from the robot arm. So this time, participants trained in two different conditions and tested in the same condition. Notice that the group who practiced under the gradually increasing forces showed much larger after effects than the group who practiced under the consistent force. And such an after effect also reduced to much slower in the gradual group than the abrupt group, which was depicted in the graph on the lower left-hand corner. What is more interesting is that the gradual group showed very slow adaptation, whereas the abrupt group showed much faster adaptation, represented by the steep curve formed by the black dots. This is a strange result because even though it looked like the gradual group achieved small amount of adaptation, they showed much higher after effect than the abrupt group. We can find out what that means if we think about the post adaptation condition. During the post adaptation, the participants were not holding the robot arm. Therefore, the after effect in this condition can be more associated with newly updated arm dynamics than that of the force from the robot arm. In that sense, the larger after effect in the gradual group means that the extent to which the internal model of their own arm dynamics was updated was greater in the gradual group than the abrupt group. So, the implication of the result is that the gradual group was continuously updating the internal model of their own arm dynamics while holding off the adaptation to the gradually changing external forces. On the other hand, the abrupt group did the opposite. They continuously updated the internal model specific to the external forces while reserving the adaptation of their own arm dynamics. In addition, the retention of the after effect was relatively longer term in the gradual group than the abrupt group. The researchers who conducted this study suggested that this is an expected result, as the internal model of the arm dynamics can be generalized to other tasks. Therefore, the motor memory associated with it is worth saving, whereas the internal model of the external force is too context specific that can be changed at any time, and it is better to make it less resilient. What does the principle of the relationship between the adaptation and the variability tells us about the current corrective exercise strategies? The exercises shown in the slide are often used to reactivate and train the force couples that allow upward rotation of the scapula. There are usually two aims of these exercises. One is to facilitate the inhibited muscles, and another is to improve the strength endurance of these muscles. Therefore, programming for these exercises should address both goals. However, in most cases, arguably, we have designed an exercise program to be suitable more for improving muscular endurance than facilitating the inhibited muscles. For example, it calls for 15 to 20 repetitions with a fixed amount of weight or resistance for 3 or 4 sets until fatigue, until the muscles are fatigued, which is based on the principle of overloading that induces physiological adaptation of the neuromuscular system. However, taking into account what we now know, we can now appreciate that facilitating the inhibited muscles would require a different mechanism than simply physiological adaptation. It requires motor adaptation that allows the brain to update the neuronal representation of the body dynamics. As we discussed in the previous slide, updating the body dynamics through exercise would require variable rather than consistent external forces or resistance. Therefore, I suggest that it would be worth considering additional options that can provide more variable resistance than traditional weights or weight plate based exercise equipment. Manual perturbation, for example, would be an effective way of changing the amount of resistance after each repetition. In addition, a pneumatic or hydraulic resistance system can also provide a convenient way of varying resistance that is also measurable. Today, I have talked about the neuroscientific theory of human sensory motor adaptation. It can be summarized as the following. First, sensory motor adaptation occurs automatically and unintentionally due to the embedded function of the internal model that reduces sensory prediction error, and we therefore have minimal cognitive control over it. Second, the central nervous system can differentiate between the predictable and non-predictable factors that affect movement based on the variability of each factor experienced, and it prioritizes the adaptation towards less variable sources as these are more predictable. And with respect to applied implications, I would like to suggest the following take-home messages. First, creating sensory prediction errors is an effective way of tapping into the brain's mechanism to induce adaptation towards specific movement patterns rather than relying completely on verbal instructions or cueing. Second, if we need to use verbal instructions or cueing, we should consider their effect on the implicit process of adaptation. And third, when using the external forces to generate motor adaptation, varying the amount of perturbation can maximize the potential to change the body dynamics that are transferable to other contexts. These are the references by subjects, and these are the resources that you can learn more about computational neuroscience and get some of the articles that I talked about. Thank you everyone for listening. Hope this was useful for you. I would be happy to answer any questions that you might have. You can email me or reach me through LinkedIn. On my LinkedIn, I uploaded another PDF version focusing more on the experimental evidence for the internal model. Okay, everyone, have a great day now.